Hello everyone, this is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Carrier Aggregation Evolution, presented by Anritsu. Our presenter today is Richard Bellairs, Product Marketing Manager at Anritsu. Just a reminder to everyone in the audience that within 24 hours of this webinar, we will provide you with a link to the recording of today's webinar, as well as a PDF copy of the slides. During the webinar, we encourage all viewers to submit their questions via the control panel, which will then be answered at the end of the presentation. At this time, I'd like to pass the presentation over to Richard.
Thank you, Kyle, and hello everyone. Thanks for taking time out to join us today. It's great to see so many of you. It's much appreciated. So I hope you find this session worthwhile. Just to give you a very quick introduction to who I am, I'm responsible for the worldwide marketing of Anritsu's protocol R&D test solutions. This means that my team works mostly with the leading LTE modem chipset and device makers to help them bring their products to market. So it gives you a kind of clue as to the angle that I'm coming at the topic from. So in this webinar, I'll be looking at how evolutions in the mobile networks affect mobile devices, which you may also hear me refer to as variously as user equipment or devices or UEs. All means the same thing, basically a modem, and we'll be focusing on the way they're tested. Now, according to the well-read Cisco Visual Networking Index, by the end of 2014, the number of mobile connected devices exceeded the number of people on Earth. And by 2019, there'll be nearly 1.5 mobile devices for every person on Earth, which is just a staggering number. The world's projected population in 2019 is 7.6 billion, but there will be 11.5 billion mobile connected devices, including M2M modules, by 2019. Now, nearly 3/4 of the world's mobile data traffic will be video by 2019. Mobile video is expected to increase 13-fold between 2014 and 2019, accounting for 72% of total mobile data traffic by the end of that period. So we know that services will become increasingly data intensive. By 2019, the average traffic per mobile connected end-user device will reach 2.8 gigabytes per month, up from just 359 megabytes per month in 2014. So the question is, how will mobile networks deliver this service? Now, in this webinar, we'll discuss carrier aggregation as one of the key technologies that's already being deployed in order for mobile networks to handle these huge increases in demand. The key points I'd like you to take away from this webinar are, firstly, that carrier aggregation is about much more than just peak user data rates. Of course, user data throughput is an extremely important metric, but it certainly doesn't tell the full story about network performance. It's emphasized in many headline-grabbing reports, but by the end of this webinar, you'll appreciate that carrier aggregation can be used to achieve several other useful objectives. Secondly, you'll appreciate that there are many ways to deploy carrier aggregation. And what this means for device makers is that they are unlikely to be able to predict or know all the situations that their product will actually find itself in once out in the real world. All the different RF environmental considerations, all the different signaling scenarios that it may undergo are impossible to predict. Yet they need to be as sure as possible that their product will handle all those conditions and perform well under all possible situations. So this means that testing becomes a huge challenge because of all the different ways that carrier aggregation, or CA as I'll probably start referring it to for the rest of the session, can be deployed. The last point I want to make is about how the available test solutions are evolving to match the evolution of the technology. So we'll start with a brief review of the fundamental concepts of CA, and it will be brief because I know that many of you will already know a lot of this stuff, but there may be some of you who have joined to understand the fundamentals of carrier aggregation. So as I'm sure most of you know by now, LTE-Advanced is a collection of techniques that evolve the LTE standard in order to address the key challenges that are faced by the industry of increasing data volumes, network congestion, and spectrum fragmentation. Some of the key technologies that we at Anritsu are concerned with when we're talking about the UE or user equipment testing are carrier aggregation, high-order MIMO, heterogeneous networks or HETNets, and coordinated multipoint or COMP. And they're just really some of the big chunks of the standard that we're looking at currently. There are many other minor features being introduced into the Release 11, Release 12, Release 13 versions of the 3GPP standard. So carrier aggregation will be the main focus of this webinar, but we need to understand that it's one tool in the complete toolbox of techniques that can be deployed to help address the challenges of fragmented spectrum allocations, increasing data demand, and network congestion. Carrier aggregation fundamentally works by increasing the bandwidth available to a communication system, to the LTE communication system, because increasing bandwidth is the most straightforward way to increase capacity. But we all know that the radio spectrum is a scarce, limited resource. Governments allocate parts of the spectrum to different uses, and mobile operators pay millions and sometimes billions of dollars for the right to use specific frequency bands. For LTE, these slices of spectrum tend to be allocated in 5, 10, or 20 megahertz chunks. In fact, 20 megahertz is the largest bandwidth defined for a single LTE carrier. So carrier aggregation enables multiple carriers to be combined in order to increase the total available bandwidth for a connection. And the 3GPP standards allow for up to 5 different carriers to be combined to give a maximum total bandwidth of 100 megahertz. These combined carriers may reside in a contiguous portion of the same frequency band, or they may be separated, that's non-contiguous. And the carriers could be within the same operating frequency band, intra-band, or they may be in completely different operating bands in totally different parts of the frequency spectrum, which we refer to as interband. So in order to perform carrier aggregation, a UE needs to be able to receive and transmit on more than one carrier simultaneously. This means that the complexity of the RF transceiver is increased, as well as the baseband processing power requirements. So a high level of silicon integration is needed to enable carrier aggregation. So as we've discussed, carrier aggregation is a core capability of LTE-Advanced. And LTE-Advanced is the label attached to releases 10 and later of the 3GPP LTE standards. The most recent finalized version of the 3GPP standard is release 12, and release 13 will be finalized later this year. Each release of the standard adds support for additional specific CA configurations. So release 10, the original introduction of CA, supported 2 downlink carriers. And release 11 then introduced support for uplink carrier aggregation, whereas release 12 continues that evolution and introduces configurations for up to 3 downlink carriers. The first release of the LTE standard was release 8, and as CA was introduced in release 10, it was important that it retained backwards compatibility with release 8 and release 9 conformant devices. Clearly, if you've got millions of devices already out there in the field, you need to make sure that they're going to continue to work. So the way it maintains backwards compatibility is by considering the primary component carrier as the anchor for control signaling and mobility management of the device. And the signaling on the primary carrier controls the addition of and release of secondary component carriers. So you have 1 primary carrier and between 1 and 4 secondary component carriers, bringing the maximum total number of carriers to 5. Note that the number of uplink carriers can be different to the number of downlink carriers. The only rule is that the number of uplink carriers cannot exceed the number on the downlink. The standard supports the use of remote radio heads, where the base station's RF transceiver is located away from the base station, and also relay nodes or repeaters. And both of these can be used in conjunction with carrier aggregation to improve network coverage. Here are some examples of how CA can be deployed in a real network. And here, I must stress, we're looking at very, very simplified examples. We are just considering the case of 2 aggregated frequencies, denoted as F1 and F2. In example 1, we have a single base station, or otherwise known as a LTE node B, which is operating with frequency 1 and frequency 2, F1 and F2, in the same defined operating frequency band. And here a CA-capable UE, which is within the coverage area, could connect on F1 and then aggregate another carrier on F2 to potentially double its possible data transfer rate. But F1 and F2 are covering roughly the same area on the ground. So in example 2, here the operator holds some additional spectrum in a higher frequency band, which allows for the delivery of high throughput to any CA-capable devices that happen to find themselves within the F2 coverage area. Example 3 shows how CA could be used to provide a more consistent user experience by using CA to compensate for poor performance at cell edges. Example 4 shows how remote radio heads could be used to provide high data throughput in targeted hotspots. Finally, example 5 is similar to example 2, but achieves a larger area of CA coverage through the use of repeaters for the second frequency carrier. The reason why I wanted to show these examples is just to illustrate how CA can be deployed in many different ways. And if we remember, these are relatively simple examples where only 2 component carriers are available. So you can start to imagine the complexity as we start to introduce additional component carriers into the situation. Now, of course, user equipment such as a smartphone will move around, and users expect seamless service as they're moving around, driving in their car, walking in an urban environment, on a train, etc. So mobility adds a whole additional dimension to testing of devices, to their operation, and testing to ensure that they will work in different scenarios. So here we see some very simple mobility scenarios, again with only 2 carriers. The first scenario on the top left shows a single base station operating at 2 frequencies. And our device starts at the edge of the coverage area, connected to just the primary carrier. It then moves into the area covered also by the secondary carrier, which is denoted as an S cell. So an LTE primary carrier is often referred to as a P cell, and the secondary carrier as an S cell. Now, in order to take advantage of CA, some signaling needs to take place between the network and the device in order to configure the secondary carrier as it moves into the S cell area. And then as the device leaves the S cell area, further signaling occurs to remove the S cell configuration and revert back to using a single carrier. This type of scenario can be tested using a LTE signaling tester such as the Anritsu MD8430A that can be used to simulate one or more LTE base stations. The relative power levels of the S cell and the P cell can be adjusted to simulate the actual levels that would be seen by a device during this scenario in the real world. We can see that there are many additional possible mobility scenarios. For example, the device might remain in the same P cell area but change S cell. It might remain in the same S cell but change P cell, and we might be changing both the primary and the secondary cells. So there are many, many mobility scenarios, all of which need to be tested to ensure that a device can cope with all that will be thrown at it when it gets out into the real world. So this presents a formidable challenge. So we've looked at the fundamentals of CA technology. Let's just recap on why CA is so important by reminding ourselves about the core benefits. First key benefit is higher data rates. So higher data rates are delivered simply by virtue of the increased spectrum usage. We're effectively increasing the width of the highway that's available for data transfer. A Category 6 device, so I should just mention that in the 3GPP standards, devices are given categories according to their maximum data transfer capability. A Category 6 device can transfer 150 megabits per second using a 20 megahertz bandwidth. And if we aggregate another 20 megahertz carrier, then it doubles to 300 megabits per second. Now also, because of the increased spectrum availability, we can choose to increase the data rate for the same number of subscribers, or we can keep the maximum data rates the same, but increase the capacity, increase the number of subscribers. With carrier aggregation, there's also less signaling overhead needed for load management. What we mean by that is we can balance the loading between frequencies to make best use of the for example, a low frequency band to provide better coverage. Without carrier aggregation, our traffic management has to rely on handovers, which are signaling procedures which are relatively slow, which take several seconds when you take into account the measurements that the UE has to report back to the network and the handover procedure. The process becomes much simpler when carrier aggregation is activated because load balancing happens as part of the packet scheduler within the B within just a few milliseconds. LTE coverage in macro cells is uplink limited because the terminal or the UE has a much lower output power compared to the typical base station power. So typical UE output power is around 200 milliwatts compared to a typical base station power of several tens of watts. So the minimum threshold is limited by uplink coverage, while the coverage could be even wider if we were considering only the downlink direction. carrier aggregation can enhance the coverage by using the low band for the uplink connection, while the downlink can still be received by the device, both on the low band and on the high band. The high band connection couldn't be used without carrier aggregation. In this way, carrier aggregation can enhance the downlink coverage of the high band. So imagine a UE connected to the LTE-800 cell in this diagram on the right here, and positioned between the vertical lines. Well, CA allows that UE to also make use of the LTE-1800 downlink, which without carrier aggregation would in effect be a wasted resource. So we've seen the potential benefits that operators can get from deploying CA. Let's look at the current state of play. What is the current status of carrier aggregation in the world today? Well, here are some data points from the GSA, GSM Suppliers Association. And according to the GSA, there are now 49 commercially launched CA networks. The majority of these aggregate to downlink carriers. Most LTE-Advanced devices are classed as Category 4 devices. This means they can support up to a total combined bandwidth of 20 megahertz, which gives a maximum theoretical downlink rate of 150 megabits per second. There are already 20 networks capable of delivering 300 megabits per second downlink speeds to a Category 6 device, and there are several devices of that capability now commercially available. Moving on from to carrier aggregation, there are a small number, i.e. 9 networks, described as being either in the deployment phase, trial phase, or test phase. Correspondingly, we can see that Category 9 devices are beginning to emerge. So the key point is that carrier aggregation is gaining traction in the market, and it's evolving very fast. So how do we expect the CA technology and the application of CA technology to develop? Well, these are the general areas where we expect to see development. So logically, there will be an increase in the number of component carriers and the total bandwidth supported, both in the downlink and in the uplink. And there'll be support for a greater number of frequency bands and combinations of frequency bands. An important area for development will be the use of carrier aggregation to enhance the support of small cells and heterogeneous networks, or HETNets. And we'll see in a second how carrier aggregation can actually help with HETNet deployments by managing interference with a feature known as cross-carrier scheduling. We're likely to see more development to enable the flexible aggregation of FDD and TDD LTE carriers. That's frequency division duplex and time division duplex, duplex modes. And finally, we'll see developments to aggregate carriers between the LTE licensed bands and make use of unlicensed spectrum. Since 2012, a lot of work has been done to develop CA devices, starting with Category 4 devices with a maximum 20 megahertz bandwidth, up to where we are today, where we're starting to see the emergence of Category 9 devices that are able to make use of 3 downlink carriers to achieve a maximum downlink rate of up to 450 megabits per second. It's not shown on this chart, but it's probable that we'll see Category 10 devices. That means they're able to simultaneously support 2 uplink carriers before the end of 2015. Then next year we'll probably start to see devices capable of aggregating up to 4 downlink carriers. If we look at the way CA has developed so far, we can state as a general rule of thumb that we can expect a delay from chipset support to service launch of around 12 months. From Anritsu's perspective, working with chipset and device makers to test their devices, we see at first hand how this time-to-market pressure creates testing challenges for our customers. Not only do they have to test the basic functions of a device, but they need to gain early confidence that it will work under real network conditions. And also, to gain market entry, they need to pass industry certification and specific operator acceptance tests. So 12 months might seem like a long time, but when you consider all the activities that need to take place within that 12 months, it really is a huge challenge for these chipset makers and device makers to get their devices to market and of course beat the competition. So in addition to adding additional carriers, each 3GPP release beyond release 10 has added further frequency bands and band combinations and bandwidth combinations to the existing carrier aggregation modes. Release 12 has added 3-band carrier aggregation and many more combinations of downlink and uplink component carriers, and more are expected in release 13. Now, along with increasing the amount of available spectrum, another way to meet increasing capacity demands on a mobile network is to increase the network density. This basically means adding more cell sites to handle more users. And this is what a heterogeneous network is intended to do, or a HETnet, which employs different types of small cell base stations within the relatively large coverage area of a traditional macro cell. The small cells can cover gaps in the macro coverage and also be used to handle localized hotspots where there's a high concentration of users. Now, when you have so many overlapping cell areas, interference becomes a major issue. Inter-cell interference between neighboring base stations and base stations that are within the coverage area of other base stations. So, in order to make an efficient HETnet, you need methods to mitigate interference from the cells that the device is not directly communicating with. Now, carrier aggregation with cross-carrier scheduling is a technique that's used to prevent control channel interference in HETnets. In the example shown, the macro cell's control channel, or the PDCCH, is transmitted on frequency 1, but schedules data transmissions on both the primary cell and the secondary cell, which is using frequency 2. The picocell's control channel also schedules data transmissions on both its P cell and S cell, but that's transmitted on frequency 2, so it doesn't interfere with the macro cell's control channel. Now, there are other interference mitigation techniques such as EICIC and FEICIC. EICIC is a technique that works in the time domain, but it requires more complex network implementation, and it requires a high performance backhaul signaling fiber link between the base stations in order to coordinate the base station activity. Now, many network operators have both TDD spectrum and FDD spectrum. For example, Vodafone in the UK has 25 megahertz of unpaired spectrum, which is suitable for TDD in the 2.6 gigahertz band, in addition to paired spectrum, which is suitable for FDD at lower frequencies. The ability to aggregate these two types of spectrum has a number of potential benefits. For example, TDD spectrum could be used to supplement FDD spectrum to provide additional throughput and capacity on the downlink. And conversely, FDD spectrum, which is generally at lower frequencies than the TDD spectrum, could be used to achieve greater range on a TDD uplink, which is often the limiting factor. The uplink power of transmission from the UE is often the limiting factor, especially for TDD coverage. So indeed, according to a white paper that I read from a small company called Acceleron, TDD is emerging as the preferred duplex mode for small cells because it promises increased capacity, reduced cost of ownership for operators, reduced spectrum costs, and improved battery life. And this type of joint carrier aggregation between FDD and TDD has been standardized in 3GPP Release 12, and companies are already forging ahead with deployment of this technology. For example, in September 2014, China Telecom announced a successful completion of a FDD-TDD CA demonstration, and more recently in the US, the Sprint Spark network is capable of delivering peak speeds of up to 60 megabits per second by aggregating FDD spectrum in the 800 megahertz region with TDD in the 2.5 gig region and also in the 1.9 gig region. Today's LTE networks are deployed in licensed spectrum bands. However, the increasing demands for capacity will require network operators to exploit all possible spectrum resources available to them. And among these resources are large tranches of unlicensed spectrum, including around 500 megahertz available in many regions of the world in the 5 gigahertz band. Now, this spectrum is not dedicated to individual network operators in the same way as licensed spectrum, and it's used by other technologies such as Wi-Fi. So the occupancy of this unlicensed spectrum can be variable and unpredictable, so it's difficult to give a predictable quality of service using this spectrum. But nonetheless, it's a valuable resource that can be tapped into. And one possible approach to using this unlicensed spectrum is to use carrier aggregation. Connections could be anchored in the reliable licensed spectrum to give reliable mobility management, while the unlicensed spectrum is used to supplement that to boost throughput and capacity when there's sufficient spectrum available in those bands. And the wide bandwidth, low power, and limited propagation of the 5 gigahertz band make it more suited to small, high-capacity cells set in the backdrop of wide area coverage that are provided by lower frequency licensed band macro cells. There are it's already being looked at and being standardized in the 3GPP standards in Release 13, which is proposing a form of dynamic channel allocation to minimize the impact between LTE and Wi-Fi in unlicensed bands, because obviously we don't want the LTE part to interfere with devices that are using Wi-Fi. So it's critical to ensure that there's no loss in performance of existing Wi-Fi devices if LTE starts to use those frequency bands. Vodafone Spain, for example, announced that it's achieved speeds of 600 megabits per second in tests of LLA, which is Licensed Assisted Access, which is how, the name of this technology in the 3GPP standards, and that was conducted with Hawaii and Qualcomm. So we've reviewed the fundamentals of carrier aggregation, we've looked at the current market status, and we've also tried to peer into the future to see how the technology is likely to develop over the next 1 or 2 years. I want to emphasize the key point that carrier aggregation brings much more than just headline data rates, and in fact it will also be a key enabler for increasing capacity and coverage through the use of things like unlicensed frequency bands, and also for enabling dense HETnet deployments. All this means that there are many different deployment possibilities that create a sizable testing challenge for device makers. Anritsu offers a comprehensive range of solutions for testing any kind of device that has LTE-Advanced connectivity at all stages of development. Targeted at device R&D labs, we have the MD8430A, the MD8480C, and the MD8475A signaling testers. that can be paired with various software applications such as our Rapid Test Designer, or RTD, and Smart Studio for efficient test creation and debugging. For 3GPP protocol and RF conformance tests, we have the ME7834 and ME7873 systems for leading coverage of all the tests that are mandated by industry certification bodies, the GCF and the PTCRB. And then operator or carrier-specific acceptance testing is also supported on the ME7834 and ME7873 systems. And those are supplemented by the MD8475A for the broadest portfolio of carrier test packages. So here's a summary of the key CA testing challenges that we've discussed. Firstly, there's a large number of deployment and mobility scenarios. Now, in order to test these in the lab, we need equipment that simulates many independent RF paths. And a single 8430A unit supports 2 carrier aggregation mobility testing, so you can do the types of scenarios that I was showing you earlier with 2 downlink carriers. To that single 8430A unit, you can add a low-cost RF extension unit to support 3 carriers and beyond. Then we have many frequency band and bandwidth combinations, so we need equipment that can handle them all. The 8430 frequency band and bandwidth configuration is completely flexible. Now, testing operation in HetNet deployments will require support for both frequency domain techniques, such as cross-carrier scheduling, and time domain techniques for interference mitigation. And the 8430A supports cross-carrier scheduling, EICIC, and FEICIC, which is for testing advanced receiver algorithms for interference mitigation. The complexity of tests and the sheer number of test variants necessitates test development tools that simplify test creation. And our Rapid Test Designer software, or RTD, is an integrated environment for test creation and management that controls test execution on a range of signaling testers. Finally, we have the challenge of running all the required tests within compressed development schedules. And this means that easy-to-use automation tools are needed to minimize test times. All our products interface with test automation tools and can automatically control the device under test. We've been talking about the future of CA. Well, Anritsu, in its close relationships with the leading carriers, chipset and device makers, is uniquely positioned to deliver test capabilities for future technologies today. So just to wrap up, carrier aggregation is so much more than headline-grabbing peak user data rates. There are many ways to deploy carrier aggregation, and this makes testing device behavior under all possible configurations a huge challenge. But luckily, there are test solutions available today, and these continue to evolve in line with the industry requirements. So now I'll turn back to Kyle for the Q&A session.
All right, thanks, Richard. We've had a number of questions come in, so we'll just jump right in. The first one, so earlier in the presentation, you mentioned technology called COMP. Does this also involve carrier aggregation? And also, can you explain a little bit more about what COMP is?
Yeah, sure. So COMP stands for Coordinated Multipoint, and it's a feature that was introduced into Release 11 of the 3GPP standard. It's really designed to improve network performance at cell edges. It's another one of these interference mitigation techniques. So, although it can be used in both traditional homogeneous networks with just macro cell deployments as well as HetNets. COMP can operate in the downlink and the uplink, but in COMP what you have is a number of transmit or receive points that provide coordinated transmission or reception. I'm talking about in the network, so in the radio access network here. So a transmit receive point is a set of co-located antennas, and these transmit or receive points can belong to a single eNode B or to different eNode Bs. The coordination can be done in a number of ways. One example is joint transmission, where two or more transmit points transmitting the same data in the same frequency at the same time, a little bit like MIMO, but on a bigger scale. And another mode is called dynamic point selection, where decisions are made to schedule the data from a transmit point depending upon the different interference conditions. Okay, does that answer the question?
Yeah, I think that sounds great. Yeah, I think that sounds good. All right, next question coming in is, do all Release 10 or later UEs support carrier aggregation?
No. So carrier aggregation is an optional feature for the UE. And what happens is the UE will signal to the network in something called the UE capability information that it transmits during its attach procedure, which is when it first registers with the LTE network.
All right, great. Another question coming in. What is the difference between carrier aggregation and dual connectivity?
Okay, so dual connectivity it is a slightly different thing. It's sometimes called inter-site carrier aggregation. What this does is it allows the UE to connect to two base stations at the same time, and it splits the user plane and the control plane data. It basically allows increased user plane capacity and increased throughput.
All right. Next question we had come in. Can you explain how carrier aggregation works between the primary and secondary cells and how this is coordinated from a signaling perspective?
Yeah, sure. So it's all coordinated from the network. So the eNode B essentially controls the UE. It signals, so the UE will connect to the network, to the eNode B on the primary cell to begin with as the primary carrier, and then signaling procedures are available to add or release additional carriers or additional secondary cells.
All right, great. Another question we had. You spoke earlier about carrier aggregation in licensed and unlicensed spectrum. Is this the same as LAA?
Yes, essentially. So LAA stands for License LTE Assisted Access, and it's the 3GPP term for CA, which involves combining the LTE licensed spectrum with unlicensed spectrum.
All right, great.
Okay.
Now, feel free if you want to continue. Feel free.
No, that's fine.
Okay.
Just carry on.
Cool. Next question. How can you test different mobility scenarios without conducting field trials?
That's a great question. If we imagine a device moving towards a single base station, then the received signal strength or power level will be the key parameter that's changing as far as the device is concerned. Now, as the device moves closer to the base station, the received power increases, and correspondingly, as it moves further away, the power decreases. So if we're using a base station simulator in the lab, then we can simulate this basic mobility by simply increasing or decreasing the power level at a rate that corresponds to the velocity of the device that we're simulating. Now, for example, an Anritsu signaling tester can simulate several base stations simultaneously, and the power level for each one can be adjusted independently to simulate the desired mobility path. So power is the main parameter we can vary. In the real world, there's also other effects, such as the distance from the base station changes, the device will see slight timing changes, and and differences in the relative timing offsets between base stations, which we can also simulate. Of course, there'll also be real RF propagation and multipathing effects due to the physical environment. These effects can all be simulated by combining a standard signaling tester with a RF channel emulator or fading emulator to create an accurate simulation of different mobility paths. On top of the RF considerations, we then need to fully control the signaling to simulate cell selection and handover procedures. So it can get pretty complicated, but it can be done.
All right, thanks, Richard. Next question we had come in. Once a secondary carrier cell is added, does it have to be activated separately in the MAC layer before the transport blocks are combined?
Yes, it would need to be activated before the MAC starts to send the transport blocks.
Okay, great. And kind of as a follow-up question, how does the service provider obtain the additional bandwidth for aggregated carriers?
Basically from the government. We'll occasionally hear about the spectrum auctions that take place. It's the government of each country that allocates the spectrum to different operators. It really depends on where you are in the world as to how exactly that gets allocated. But typically there are spectrum auctions held, and operators have to bid for different parts of the spectrum.
Okay, great. Next question coming in for intraband. Are there any specific testing requirements that need to be considered between a contiguous and a non-contiguous configuration?
No, not well. Of course, the test platform itself has to be able to support the primary cell and the secondary cell in different frequency bands. An Anritsu 8430, for example, has 4 independent RF units, so it can actually, with a single unit, we can actually simulate 4 different carriers in different frequency bands. So, yep, you just have to make sure that your network simulator can support that operation.
Okay, we have time for just about a couple more questions. So, are Cat4 devices capable of carrier aggregation?
Yeah, Cat4 devices basically do carrier aggregation up to a maximum of 20 megahertz. So, for example, they could aggregate 2 5 megahertz frequency bands or 2 10 megahertz frequency bands together. So, yeah, the maximum data rate for a Cat4 device, I think, is 150 megabits per second.
All right. Next question: have any carriers that in the U.S. that you know of employed EIC yet? And if so, how do you identify it in testing?
I'm not sure if any carriers have deployed it. Also, I'm not really sure what the how do you identify it in testing means. I'll answer a slightly different question. Mm-hmm. So I'll answer the question of how we can test it using a network simulator. And yes, we can. EICIC is all about generating what's called almost blank subframes in the LTE data. So it's time domain coordination. So what happens is we mute the macro cell in order to and then schedule data transmission on the small cell during these almost blank subframes, which is so it's in effect muting the interfering cell to give the other cells a chance to communicate.
All right, great. I think we have time really just for one more question, so take us out. In order to implement the carrier aggregation concept, does the base station have to have an independent RF chain?
Uh, yes, if it's for interband carrier aggregation, then yes, it would obviously need to be transmitting at different frequency.
All right, great. That's about all the time we have. I want to thank everyone for attending today's webinar, Carrier Aggregation Evolution, presented by Anritsu. Again, our presenter today was Richard Bellairs, Product Marketing Manager at Anritsu. Thank you, Richard.
Thank you very much.
All right, have a great day, everyone.